In the third lesson of the section titled Extending the VLab Environment with VR Affordances of the Development of a Virtual Lab for Programmers course, you will learn how to set up a basic VR-enabled project from scratch, using the XR plugin framework and the XR Interaction Toolkit and its sample assets. This is quite important for understanding the purpose, role and function of each individual component offered by those packages. So, instead of using prefabs for entire, fully functional controllers and other elements of a typical VR application, we will use the minimum required to set up one such application from scratch. We will also learn what the minimum required configuration is for those components to work given their default configuration as part of the XR Interaction Toolkit. Begin with an empty 3D project. The project only contains a directional light and a camera. Then, install the XR plugin framework under Project Settings, XR Plugin Management. Next, enable a provider plugin suitable for your equipment. For this lesson, we will use the OpenXR plugin. Note that there are several issues that need to be addressed, as reported by the project validator. We will deal with those later. Next, import the XR Interaction Toolkit via the Package Manager. Search for XR Interaction in the Unity registry. Also, install the starter assets under Samples. The first issue reported by the project validator is that there is no controller profile selected for the OpenXR plugin. This is necessary for the plugin to be able to read input from your controller of choice correctly. To address that, go to the OpenXR plugin's settings, add a new interaction profile and choose the right controller. For this lesson, we will use the Oculus Touch profile. The remaining issues are mere warnings and beyond the scope of this lesson. We will simply ignore them for now. Next, let's create a simple floor. We will not spend more time now to shape and style the floor because, as explained earlier, the purpose of this lesson is to showcase how a functional VR application setup can be achieved with the least amount of structure, components and configuration possible. Remember to save the scene frequently. The next step is to create a VR-enabled camera and relevant structure. To do so, choose XR Origin, VR, under XR on the context menu. Notice that a hierarchy of 3 game objects has been created, which also includes a camera. This is the camera that will be used by the application to render the VR space, so the pre-existing main camera can be safely deleted. Also notice how the newly created camera includes a tracked pose driver component. This is the bridge between the immersion device to be used and the camera's position, orientation and tracking state. The inputs required are predefined and do not require any further configuration. The camera offset game object will be used automatically to correctly set the camera height according to the XR Origin's configuration and the user's actual height, if desired. The XR Origin component is the actual representation of the user's immersive viewpoint within the virtual world. Notice how the structure also contains an Input Action Manager component. This is because all components used in this lesson are designed so as to work with Unity's input system. The Input Action Manager component guarantees that the necessary action maps are enabled and available to all components working with the input system. Let's run the application and verify that the user is actually immersed in the virtual world and that head tracking works as it should in positioning and rotating the camera in the scene. Next, let's create a right-hand ray for interacting with objects, navigating, etc. Go to the Controllers folder under the XR Interaction Toolkit Starter Asset Prefabs. Grab a XR controller right and drag it onto the camera offset game object so that it is at the same level as the main camera game object. The prefab contains an animator component that animates various elements of the controller's visual appearance as you physically manipulate them. It is pre-configured for the standard set of controls defined by the chosen controller profile. Notice the structure beneath the XR controller right game object and how it contains 3D elements for the entire controller, including its body and all of its controls. In its current state, the controller's representation does exist in the scene and can be animated, but it does not follow the position and orientation of the physical controller used. To fix that, we need to add the necessary functionality to track the physical controller and appropriately transform the controller's virtual representation. To do so, add a tracked pose driver, input system, to XR controller right. This is the same component used to achieve head tracking and camera control. Configure its inputs to work with references to already defined input actions. Locate appropriate actions for positioning, rotating and state tracking of the controller from within the sample input actions provided by XRI, namely, the position, rotation and tracking state actions of XRI right. Drag them onto the respective fields of the controller's tracked pose driver. This is all that is required for the controller to be properly positioned and oriented in space. In addition, its controls animated as needed. Let's run the project to verify that. We shall now enrich the controller with interaction abilities. First, let's add a visual element to assist interaction, namely, a ray originating from the controller's body. Add a XR Ray Interactor component to XR controller right. This is the component that actually provides interaction capabilities. The component offers numerous configuration options and is designed to be able to address a vast variety of needs and use cases. Now, we should add a visual appearance to the controller's ray. Add a XR Interactor Line Visual component. This is the component that will handle the parameters of the visual appearance of the ray, while the actual line rendering will be handled by a line renderer that is automatically added as a dependency of the XR Interactor Line Visual. To configure the ray's appearance, adjust values on the XR Interactor Line Visual, not the line render directly. Let's check out the newly added ray, which, again, is in a rather primitive, default state. To facilitate next steps, let's add the ability for the user to move around the scene. The necessary element for all forms of navigation around the scene is a locomotion mediator component directly on the XR origin. Notice how our XR body transform component is also added automatically as a dependency. The former is the gateway to the user's avatar for all other components involved in locomotion-type navigation, while the latter encapsulates the logic of responding to locomotion-related input by actually transforming the avatar. As a first form of locomotion, let's add the ability to turn left and right in discrete steps. Add a snap turn provider component to XR controller right. This should be enough for the user to be able to turn. Let's verify that. Nope, it isn't. This is because we did not configure the turn provider to actually receive input from the input system. When setting up project structure by configuring multiple components all over the scene hierarchy, such omissions are very likely to happen. To fix the problem, choose the XR right locomotion turn action and drag it onto the right-hand turn input field of the snap turn provider. Everything should now work as it should. Still, the user is stuck at the same location and cannot move around. Let's fix that by adding the ability to teleport anywhere on the floor. We first need to add a teleportation provider component that will handle all teleportation-related functionality, input and configuration, just as in the case of the snap turn provider before. Next, we need to configure the XR Ray interactor with necessary parameters for the teleportation interaction. We chose to control teleportation with the trigger, which corresponds to the activation action in the ready-made input action map offered by the XRI samples. Also, the teleportation provider is designed to engage the teleportation functionality when a teleportation target is selected. Therefore, we shall set the select input field of the XR Ray interactor to XRI right interaction activate in order to instruct the interactor to generate selection events when the controller's trigger is used. This is a design choice and, again, here it means to showcase functionality with minimum configuration. We also need to define a teleportation area. The user will be able to teleport anywhere on that area. To do so, add a teleportation area component to the floor. This is all that's needed for basic teleportation to work. Let's test that. Notice how the combined, basic, functionality of snap turning and teleporting allows the user to actually navigate anywhere in the scene. Let us now create a simple interactive object that can be grabbed, moved, turned and thrown in a physically realistic way by the user. First, create a simple cube and position it in front of the user. Add a rigid body so that the cube is affected by physics. Also, add a XR Grab interactable component. The component offers extensive configuration options, but we need to adjust none right now if we seek minimum functionality that is possible out of the box. That's it. Let's see if we can actually grab, move and throw the object around. As practice, you should be capable of reproducing all of the steps in this lesson and come up with a basic project with the functionality described here after minimum configuration without the need to refer to this lesson's material or other documentation. Also, try to experiment with the configuration of the XR-Ray interactor, its visuals, the grabbable cube's parameters and the configuration of all elements involved in teleportation to get a better feel of what they can actually do.